Hello everyone, welcome to the first lecture of the fourth week. So now we are in the fourth week. In the last lecture of the third week, that means the fifth lecture of the third week, we have seen and we have explored the infinite series examples and one or two theorems which are very important, that is Cauchy general principle of convergence of a series, as well as uh, we have explored and applied those theorem in proving the convergence or divergence of an infinite series. Now in this lecture we will have different type of tests. You need to read 4 tests, that is comparison test, then Cauchy root test, then real numbers ratio test, and then rabbit test. One by one we will see in one lecture. So this lecture contains only comparison test. Comparison tests are in general two types, the first type and the second type. Comparison, already name suggests that we are going to compare the two series each term by term, right? And then we have a limit form comparison test, and that is the whole lectures outlined. So let me start with the first type of the comparison test. So consider two series un and vn. So sigma un and sigma vn are two infinite positive term series. What is the positive term series? That means each un is greater than and equal greater than 0, positive term series, right? Similarly, each Vn is greater than 0, and that's what positive term series means. What is the advantage of the positive term series? The advantage is quite easy. And now you can have this each S1 is equal to U1, S2 equal to U1 plus U2, S3 equal to U1 plus U2 plus U3, and so on. Sn is equal to u1 plus u2 plus of u3 and so on plus un, right? Look at the structure. U1 is positive, so S1 is greater than 0. U1, U2 is positive, so this is greater than 0. Not only greater than 0, but this is greater than U1 as well. Similarly, this is greater than U1 plus U2 as well. This is greater than all those series. So this means S1 is less than S2 is less than S3 and so on, less than Sn. Such a sequence is called monotony increasing sequence. So that means for a positive term infinite series, the nth partial sum, the sequence of the nth partial sum of the series is monotony increasing sequence. To test a convergence, we only need to prove that this sequence of this Sn is bounded above. That is our idea, and that is what is given already. That's why it is important to learn positive term infinite series. So considering capital sigma un and capital sigma vn are two positive infinite series, and let k is not equal to 0, a non-zero number k, which is a fixed real number independent of n, and there exists a positive integer m such that each un is less than k into Vn, and k is non-zero number, right? Remember this one. U3, if you compare U3, you have to compare by V3. This means I am comparing this inequality term wise, not something U3 is less than k into V5, no. So I am comparing this by term wise, and that is important, right? And this is true for a given fixed positive integer m. So after this fixed positive integer m, for each term of these two series un and vn, you can compare this one, and if it happens un is less than k into vn, then if vn is a convergence series, that leads to un is a convergent, and if un is divergence series, that leads to vn is divergent. That is a theorem, that is the statement of the theorem. I believe that you understand the statement of the theorem, that if bigger one k into vn, so the right hand side is convergent, then that leads to the smaller one, that is un, and if the smaller one is already divergent, then that leads to the divergence of the Vn itself, right. So that's what say. Now the proof is quite easy. So I chose it is given. So for n equal to m, so I fixed m as a positive integer. So for n is greater than equal to m, I will have Sn. Sn is equal to u1 plus u2 plus un, and this is the nth partial sum of the capital sigma un series. And similarly, I have named Tn, Tn equal to v1 plus v2 plus vn. This is also the nth partial sum of the series sigma vn. So Sn minus Sm, I am calculating Sn minus Sm. This is nothing but m plus 1 to un, right. And this is less than equal to um plus 1. Um plus 1 is given here. Um plus 1 is k into Vm plus 1. Um plus 2 is less than k into Vm plus 2. Un is less than k into Vn. So this will comes out to be k into Vm plus V2 plus Vn. So that means that is here Tn minus Tm. These are the nth partial sums. These are the nth partial sum of Vn, and these are the nth partial sum of series un, right. So overall we have here as Sn minus Sm is less than or equal to k into Tn minus Tm, right. So I can write this one as Sn minus less than or equal to k into Tn minus k into Tm plus Sm, and we can make this as a some constant. So k into Tn plus of some h, where h is nothing but it is Sm minus k into Tm. A finite quantity. This is a finite quantity. So in other way we have k Tn plus of h. Is it okay? Now if Vn is convergent, case 1, we are dealing with the case 1. So if suppose Vn is convergent, that means each nth partial sum of this series Vn, that is sequence Tn, is convergent. And I had already told you that if a series has a positive term series, if the sequence of the nth partial sum is a monotony increasing sequence, and if it is a convergent, that means it is a bounded above. So that means Tn is bounded above. Tn is bounded above. So let's say Tn is bounded above by some number b here, and this is true for every natural number n. So therefore Sn is what? Sn is less than k into Tn plus of some number h, and now Tn is also bounded. So Sn is less than k into some number b plus of h, and this can be converted by some other number b dash or somewhere else. So this means Sn is bounded above, and Sn is monotony increasing sequence, and henceforth Sn is converging series. So Sn is converging series. And what was the Sn? Sn was the nth partial sum of the series summation un. And that means the series un is convergent. That's the easiest proof. Now case 2. So suppose un is divergent, then the sequence Sn of its nth partial sum is not bounded above, so that there exists a number how much large. So capital G be any number however large, and there exists a positive number m0 such that Sn, each Sn is greater than that number G for every n is greater than or equal to m0, right. So thus from n, choose the maximum of m and m0, and then this will gives you Tn is greater than 1 by, so we have Sn is less than k into Tn. So that means Tn is greater than or equal to 1 by k into G minus of h, where k is not equal to 0, right. So this means Tn is not bounded. Tn is not bounded. this is not bounded above, right? So henceforth Tn, the sequence Tn is not convergent, and henceforth that means sigma Vn is a diverging sequence. So apply this theorem to test convergence of the given series. So that series 1 plus 1 by factorial 2 plus 1 by factorial 3 plus 1 by factorial 4 is convergent. So I am going to show summation factorial 1 by factorial n is converging series. So we are going to use one inequality, we call it factorial n is less than 1 by 2n minus 1. That is our idea. Now look at this one here. So the 1 factorial 1 is equal to 1, 1 by 2 factorial is 1 by 2, 1 by 3 factorial is 1 by 3. So clubbing all those, the left hand side is less than 1 plus 1 by 2 plus 1 by 2 square plus 1 by 3 2 ka cube plus 1 by 2 to the power 4 and so on, right? Thus each term of a given series after the second is less than the corresponding term of the convergent geometrical series, and hence by comparison test geometrical series is convergent, right? So that's why it is a converging series, because its sum is 1 by 2 less than 1. So that's why it is converging series. Now look at a very important question. A series 1 by log 2 pi power p plus log 3 pi power p plus so on log n pi power p, the nth term is this, is diverges for p is greater than 0. So we are interested to find out the sum of this log n pi power p, where p is greater than 0 is not a converging series, but it is a diverging series. Well, for that we use the limit. So evaluate limit n tends to infinity log of n pi power p divided by n. This is equal to 0. We all know that, right? And that means that will give you log of n pi power p by n is less than 1. So this is less than 1, this is less than n, right? So that means 1 divided by log of n pi power p is less than 1 by n, and this is true for every n is greater than 1. So let us compare the given series with the diverging series 1 by 2 plus, the series 1 by n, 1 by 2, 1 by 3, 1 by 4 and so on. Since each term of the given series is greater than the corresponding term of the divergent series, see here, right? Therefore, the given series is diverging. Now, second type of the comparison test, the statement says that if there are two positive term series un and vn, and there exists a positive integer m such that for n is greater than or equal to m, we have un by un plus 1 is greater than or equal to vn by vn plus 1. Now you can look at the ratio of the terms, these are the ratio of the two terms un and un plus 1. Then un is convergent if vn is convergent, and if un is divergent, then vn is divergent. How to prove? Proof is quite simple. Let Sn be the sequence, of nth partial sum of series un, and similarly Tn is the nth partial sum for the series Vn, right? Then for n is greater than or equal to m, we can have um divided by un. So this can be written as um divided by um plus 1 into um plus 1 divided by um plus 2 into um plus 2 divided by um plus 3 and so on where un minus 1 by un. We can write this one. Now why? Because this will, all these are the cancel or intermediate term. So we have um by un. Each term um by um plus 1 is greater than what is given here. See here, greater than. So each term um by um plus 1 is greater than or equal to Vm divided by Vm plus 1. Vm plus 1. Similarly, um plus 1 by um plus 2 is greater than or equal to Vm plus Vm plus 2, right? So that means if you cancel out these intermediate terms, you will get Vm by Vn. So that means we have um by un is greater than or equal to Vm by Vn. So now take un that side. So um into Vn divided by Vm is greater than or equal to un. So un is less than number. Now look at for a fixed m. For fixed m, um by Vm is going to be a fixed quantity. So each un is less than or equal to some fixed quantity k into Vn, and k is what? K is here um divided by Vm. So this is a fixed quantity, right? So that is the same statement as we have for a comparison test 1, first type of the comparison test. So by the comparison test 1, we can have the same statement as in the comparison test 1. So this was the statement in a comparison test 1, that if summation un is convergent if summation Vn is convergent, and summation Vn is divergent if summation un is divergent, and henceforth the proof is done, right? Now what is the equivalent statement? We can write in other words, if two series un and Vn of positive term series, there exists a positive integer m such that un plus 1 divided by un is less than Vn plus 1 divided by Vn for every n is greater than or equal to m, then un is convergent. Here we have changed the inequality due to the we have changes in the first statement. We have changed un by un plus 1, which is greater than or equal to Vn divided by Vn plus 1, right? Here we have changes this ratio, that's why the statement the inequality has been changed. You can write this one un by un less than or equal to Vn plus 1 divided by Vn, right? So this is the same thing. Now use this theorem to prove that the series 1 by n square is convergent. So firstly, the one series is given un. Now I will identify the series, the next series, so that we can have the comparison of this one. So here un equal to 1 by n square and Vn equal to 1 by n cube, and un plus 1 by un you can calculate it, and it will comes out to be, I mean we can calculate very easily, n plus 1 ka whole square by n square. So this will comes out to be n divided by n plus 1 ka whole square, right? And Vn plus 1 by Vn is n divided by n plus 1 ka whole cube. Now un plus 1 by un is obviously less than Vn plus 1 divided by Vn for every n is greater than or equal to m. I mean taking n as a very large number, this will true, right? See here, this is the true. So this means 1 by n cube is a p series, the harmonic series, the p series, and p series p is p here as a 3. So that is greater than 1, so it is converging, and henceforth 1 by n cube is a converging series, and therefore for sufficiently large n, 1 by n square is also a converging series. So that's why 1 by n square is going to be converges. Now using these two comparison, first type and second type, we will have a limit form comparison test. So considering two positive term series sigma un and sigma vn, such that limit see here why its name is here, due to the limit n tends to infinity un by vn equal to L is given, where L is a non-zero number. L is a non-zero number. So once you have a limit which is non-zero, the ratio of the two terms from one series to another series, that means you are looking for a limit of un by vn which is not going to be 0, that is equal to L, which is not going to be 0. Then both series behave equivalently. That means either both series converges or either both series diverges or both series oscillating. So how to prove this one? So case 1 where we consider L is greater than 0. Now look at here, if I choose here 0 and I choose here this L here. So if L is greater than 0, I can subtract some epsilon and I can have this L minus epsilon still greater than 0. Let it name it some alpha. So L minus epsilon is alpha something, if I have name it. So taking limit un by vn equal to n, therefore there exists a positive integer m by definition. So that means we have un by vn limit is equal to L will imply simply that for a given epsilon is greater than 0, there exists m such that un by vn minus L modulus is less than epsilon for every n is greater than or equal to m. And that means here un by vn minus L modulus is less than epsilon for every n is greater than m. That means L minus epsilon and L plus epsilon will be a bounds for these series un by this terms here, right, strictly less than and strictly positive, right. Now you can simplify it and you will get L minus epsilon into Vn is less than un is less than L plus epsilon into Vn, right. Now use this one, remember this is the inequality which is quite important, that is why it is equation number 1. So case 1, if Vn is convergent, let us suppose that series Vn is convergent. Once Vn is convergent and un is less than L plus epsilon into Vn. So this is the same thing as k into Vn, right. So un is less than k into Vn. K is the fixed non-zero number, k is the fixed non-zero number. Since L is non-zero already given here, right, L is non-zero, therefore here k is also not 0 as L is not equal to 0, right. So it is a fixed number. So it is what? It is the first type of the comparison test. So by the first type of comparison test, if series Vn is convergent, that leads to series Un is also convergent. So that means both series converging together. Similarly, using this theorem, L minus epsilon into Vn is less than Un. So that means here, if un is diverging, then that leads to the series Vn is diverging, and that means both behaves like equivalently. Now look at some problems. So investigate the behavior of the series whose nth term is sin n. So we are here for sin 1 by n, and so let un is equal to this, series un equal to this, and series Vn equal to 1 by n. Now comparing, find out the limit of un by Vn. Un is given, that is equal to sin 1 by n by 1 by n, and limit n tends to infinity. In that case it is 1, which is not equal to 0. So that means by limit form comparison test, the sin 1 by n is divergent, because 1 by n is divergent, we had already proved that. So thank you so much, and if you have any doubt, go through the lecture number 5 of the third week, that will introduces the whole infinite series and some important infinite series and their convergence. So you have to remember the P series and you have to remember the geometrical series, their convergence and their condition for that convergence, right. Once you have then using the comparison test 1, first type, second type, and the limit form test of that comparison test will certainly helps to investigate the convergence of the infinite series for a given problem. So once again, thank you.